you. I just popped in for a pint. And then he started that. And now it's going to be very exciting for me just to find out if the slides that I sent them at some point actually work. I suspect the answer is no, so I'm not going to look that way. It took them about 2 hours to set up the projector, so that's right. Right, so let me tell you what I did earlier today. I took part in a university thing inspired by this thing on June 23rd. Okay? Because the university discovered that we have working for us people from all the EU member states. Okay? So someone thought it would be a fantastic idea to find one of these people from each country and then get them together in a room. And so in a feeble-minded moment when I got this email, I said, yes, I am Swedish, and yes, okay, I can do this. Right? Yeah. So this afternoon I showed up, and on the floor were a bunch of t-shirts with different flags with different countries. Which first was like an IQ test, trying to identify the flag for your own country. And then it turned out that Bulgaria was ill. Spain didn't want to wear the t-shirt because it was the rolling flag. It wasn't looking good. And then what they did, they put us on the floor and said, stand here and look happy in a big bunch. And then Great Britain said, I'm leaving now. And the guy said, really? And actually, almost, we managed to convince him to stay. Okay, so that's very smart. And then we all reached the climax when the guy who was a producer from ITV said, how about if you all hold hands and people are, and walk around in a circle? And then someone said, shall we sing Ring Ring the Roses? And he said, yes, you could. And so actually my day has been ridiculous already from early in the afternoon, so this can only get better. Whereas in your case, it can go downhill from here. Okay, so anyway, welcome to tonight's seance. We will be visiting what happens after life, in a very particular sense. And so I'm going to be talking about, setting the scene pretty much for the second talk, which is much better than mine, because it's by one of our students, and they're always much sharper than the professors, as I'm sure most of you know. Okay, so I'm going to be talking about neutron stars. My plan is to introduce the idea of what these things are. I'm telling you a little bit about the questions that we're interested in, and I'm going to, there's going to be, because I'm a maths professor, okay, you do understand that will have to be a test at the end. I put as many equations as I could fit on each slide to make sure that you don't understand anything at all. And then I have some images just to keep you on touch. Okay, so basically, as you know, ever since mankind was in its cradle, pretty much people have stand up in the sky trying to understand the constellations and being inspired by the stars for everything from astrology to anything. And it used to be the case, up until something like 50 years ago, that we thought the universe didn't really change very much. The stars just gliding across the firmament, nothing much happened. And what we've learned in the last 50 years is that this is not at all true. The universe is a violent, frightening place where stars explode, galaxies collide, the universe itself was born in the Big Bang explosion 14 billion years ago and so on. And so, the kind of what we're interested in my group is in how do we understand what happens when stars die and what can we learn from these zombie stars that form what happens a second part of the star's life after death, if you like. So that's what I'm going to talk about. And so we know, actually we have known for a long time that stars live and die. So normal stars, like our sun, not very heavy, essentially burn nuclear fuel from hydrogen to helium to higher elements until they run out of fuel. When they run out of fuel, they puff up, so our sun is going to swallow the Earth and swallow the that. at some point in the future, and then it's going to shrink away to something we call the white dwarf. White dwarf is pretty boring. I have to say that because I don't work on them. You have to, in academia, pretend that it is a little bit exciting when you do, because otherwise the students find out immediately, and they're the ones that are supposed to be very excited when you do. Okay, so the white dwarf is a star which is held up by the atomic nuclei. You can imagine taking your matter and compressing it and letting gravity win all the way up until the electron shells around the atomic nucleus start pushing on each other. It's held up by something we call degeneracy pressure. It's a fancy word, basically saying the electrons push so that gravity can't win. A bigger star, maybe 10 times as heavy as the Sun, will not go out in this sort of feeble-minded fashion. It will go out in a big explosion called a supernova. And so the first supernova that we know of happened in 1054 AD, and we know that because Chinese astronomers, or astrologers, as it were, have records from that time, or we have records from that time, in China, showing that in 1054, a star in a certain constellation, there was a new star in a certain constellation. And so if we fast forward to today, this is what that region of the sky looks like if you look at it from the Hubble Space Telescope on the left, and actually with close up on the right. This is called the Crab Nebula. So this is the remnants of the explosion from 1054. False colours, the sky doesn't really look like that. If we zoom in on, no, we don't do that. Maybe I should drive. If you look, one of these dots here, you can barely see, is another kind of star, a neutron star. Okay? So in the neutron star, we continue pushing after the explosion what is left, if you like, because you throw it off, but suddenly it collapses under gravity. And in the neutron star, the mass is so wins over, so the gravity wins over this pressure of the electrons, keeps on pushing until the atomic nuclei start essentially holding each other. And these are neutrons and protons, the kind of fundamental building blocks, which are holding up this orbit, which means that this is very, very tiny. And the typical neutron star is something like 10 kilometers in radius, so that is something like a small city, or maybe you can squeeze one of these inside the M25 in London. It weighs something like a bit more than 1.5 times as much as the Sun. Now you can do this calculation. What happens if you try to cram that sort of matter into that sort of volume? I'm going to come to that. But basically, these guys are more or less the definition of the extremes of physics as we know. So we see them not because they shine, because they don't burn nuclear material anymore, they don't shine. They are very, very hot, but they're also very, very small, so we don't see them usually in light like that. But we see them because they have strong magnetic fields. You can imagine taking the Sun, which has a very weak magnetic field, but compress the Sun until it's that small, basically conserving the amount of magnetic flux that you have. And when you get down to that sort of small volume, then the field is enormous. So these are the strongest magnetic fields we know of in the universe. Something like 14 orders of magnitude stronger basically to that in the Sun. So that's enormous. Much, much stronger than we can create on Earth. But in reality, they are just like normal toy magnets. They go north and south pole. If you spin them around, they will radiate electromagnetic waves. And so here is a picture we took of one last week, or maybe an artist's impression, which seems most likely, because I don't think they are likely to be blue, although blue is kind of tricky. Which is why many people will be using this particular image this evening and maybe tomorrow, who knows? I'm just guessing. And so as this guy rotates around some axis here, because it's not aligned with our axis, it will emit electromagnetic waves and it will slow down. And so we see these guys, and we have seen this in the 1960s, something called radio constant, an extremely precise cosmic clocks. They spin around, in the case of the crank pulse, so it spins around once every 33 milliseconds. Technological aim is only that it spins around in a tiny fraction of a second. So that's pretty cool. And so what happens is it emits electromagnetic radiation and it slows down very, very slowly. And so it's actually from the fact that we see the pulses from these guys, we see them slowing down, and we can figure out that they have to have a magnetic field, and we can try to figure out how strong that magnetic field is. Doesn't come again with name, but that operates again for astronomers and I'm not mathematicians, so I'm not going to say. So this is the game that I play. I'm trying to figure out what happens if you take that amount of matter and you squeeze it down to that tiny bit of volume. So here's a calculation you can do. In fact, if you use this calculation together with the question over there, you can figure out how many elephants does a pint of neutron star matter weigh. So the calculation you can do is you can ask how dense is this matter, and if you want to make a neutron star at home or that kind of material, you need to take something like 50 million elephants and squeeze them into this kind of one. Now the elephants might not like that, so I suggest you go and try it at home, and also 50 million elephants cost more than 50 million units of money. So don't do this at home. If you want to do it at home, I don't suggest that I said you should. Okay? I completely wash my hands of this idea. Okay, so what happens is, basically, we can't create this matter in our laboratory. This is way beyond what we can create matter. And so, the neutron stars provide us with a way of figuring out what happens in nature if we get that sort of extreme. Of course, unfortunately, these guys are hands-off laboratories. We can't go out to kick one to see what it does. If we do, of course, fortunately, if you're a sort of crackpot scientist like myself, it's kind of good that no one can actually test your ideas. Right? So everything goes. And sadly, in my business, that is almost true. Pretty much any idea that has ever been proposed to what these guys could be is still on the market. Although we're learning, so we're doing that. So here is another view, which I think will connect a little bit with what's going to be part of the topic later, the Large Hadron Collider. So you know we spend a lot of money building a Large Hadron Collider, to smash protons and things together and learn about, again, what happens at extreme densities. So what happens when you compress matter to tiny volumes. And so, if you draw a diagram like this, I have to have at least one diagram. You're not supposed to have diagrams, but I like diagrams, so I have one. You draw the temperature in some funny scale, basically from something that's really cold to something that's extremely hot. This is just so extremely hot, you can't imagine how hot this is. It's like summer in Greece, a little bit more. Actually, this is like summer in Greece, and this is just a little bit more. Actually, this is so a little bit more that the sun is somewhere here, and this is just more. Over on this axis, we've got something called the baryon chemical potential, GeV. That's a fancy word for really dense. I don't mean thick, like that dense, just dense, heavy, if you take a certain volume. And so, normal nuclei, this is called from atoms to something or other, here's the atoms, okay? Atomic nuclei are roughly here in this diagram, this green thing in there. What the Large Hadron Collider is doing is studying matter, or creating matter at very high temperatures, but quite low densities, so up in this corner. We're probing with the Large Hadron Collider, and we find things like the Higgs boson and so on, what goes on over here. Neutron stars are very cold on this scale, but very, very dense. So they sit over here. So essentially, neutron stars provide us with nature's own Large Hadron Collider experiment, although we can't drive it. Okay, so here's my cartoon, and I just want to show you this because it's got such small tiny writing that not even I could read it when I typed it up, and that was a bit unfortunate, so I don't really know what it says. But what I'm trying to do with this is just give you an idea of how freaky this kind of thing can be. This is, I'm going to try to spend a little bit of time talking about what kind of physics we are trying to learn from these kinds of things. So, first of all, we've got this magnetic field that pokes out of the star. The reason why we see many of these. And so here, we're probing electromagnetism that is also tested in things like fusion tokamaks and those sort of things. But these magnetic fields are much, much stronger. So we're testing things like quantum electrodynamics and just box standard electromagnetism if you want. But then if we start at the very surface of this cake, it's iron. Just normal iron. Rust-free. With a tiny, tiny, tiny hole there, or maybe a few meters. We go deeper, we get more and more neutrons, tiny nuclei that don't have charge. And at some point, not very far in, these neutrons don't like to be in atomic nuclei anymore. They leave the nuclei and form a gas that coexists with the other nuclei. Right? And then we keep on pushing, these other nuclei are still so tightly compressed that they can't move, they are sitting in what we call crystal. But at some point, the density gets so high that they can't stay like that, they just become a gas as well. So now we've got the neutrons that already were a gas, now we've got the protons, the charged guys, also forming a gas. This is a very ordinary kind of thing. And then we keep on pushing because we're not the kind of people that give up. So we keep on compressing, and now we're about halfway into this object. And that's when we have no idea. Everything goes. If you like quarks, who likes quarks? You stick in the favorites, up, down, top. Charm, strange. There you are. Kind of suspected those two would come up. So if we keep on pushing, remember what I said, the white dwarf, the electron shells are holding the thing up. The neutron star, the atomic nuclei, neutrons and protons are holding the thing up. But what happens if you keep on pushing? What happens if they can't hold things up anymore? Well, the next thing are the quarks that make up the neutrons and protons. So we think that something like halfway into these stars, we will have a quark plasma, a gas from quarks that don't sit together anymore to form some weird gas. And we're trying to something. And that would be a large, sort of 7 kilometer size ball made of the kind of thing that the Large Hadron Collider make in minute samples. So we're big. Okay, so what we do with this is we try to test our ideas of what this matter could be against observations. And so we see these things now in many different ways. They manifest themselves in many different ways. They come in different flavors. Well, flavors might not be the right word, but anyway, you see them in different guises. Some of them have strong magnetic fields, some of them are weak, some of them rotate fast, some of them not so fast, some of them are a little bit hotter, some of them are a little bit not hot. And so on. And so, the problem is, when you put our theoretical ideas to the test, it's very nice if you have one idea and one observation to test that idea. That's what you can do in the laboratory on Earth. you send the lab up to test whatever it is you want to test. Right? But here, the cosmos is the laboratory, and we don't have a choice. We just get whatever we get, and so the problem is we get all the theoretical physics that we have in one place, and we have to just try to figure out how this mishmash of ideas that we may have, that we may or may not believe in, how they can explain or not what we see. So the problem is that we're mixing electromagnetism, because these guys are magnetic, as I said, we're mixing something called the strong interaction, which decides what matter is made of, and we're mixing the weak interaction, which decides how fast things cool and what the friction is and so on. And those are three of the fundamental forces in nature. And then we have number 4, my favorite, because I work in the gravity group, gravity. So we have Einstein's theory of general relativity, which I'm not allowed to talk about because that's a topic for tomorrow. But I'll talk about that anyway because I don't care. And I'm the head of group, so they can find me if they want to. And so what I want to talk a little bit about is how we use these neutron stars to test our ideas of gravity, or rather Einstein's idea of gravity, that it is made, that gravity is due to the space and time being one. Okay? So the best test bench for this theory with neutron stars is when you have 2 of them going around each other. So basically, the 2 of them go around each other because they feel the curvature of space and time that the other one creates. And the best laboratory for gravity with neutron stars is called a double pulsar. There's 2 of these pulsars going around each other, and we see the pulses from each of them. And this is an extremely unique system, because first of all, the stars are pretty close. Not as close as in the example I'm going to show you in a minute, but pretty close. And secondly, the pulses from one of them passes pretty much through the other one. So it's radiated in plane. They go around like this, and it radiates in that plane. So every now and then, those pulses go very near the other one. Okay? So if you look at something like this, here's another photo we took earlier. Again, the stars are blue, so this is looking good. You couldn't get the same guys. But here you sort of see this idea of curved space-time, which is completely fraudulent, but is the way we image these sort of things. And now imagine that the pulses from these guys, which are regularly spaced, when they come to us, first of all, they fall into this well of gravity, and then they try to climb out of it. So what happens when they do that is that light gets a little bit tired. Because light is a little bit like a mathematician, it's fundamentally lazy. Right? So if it has to climb uphill against gravity, it gets a little bit tired, and so these pulses arrive a little bit later than they do when you're pointing somewhere else in this plane. This is called Shapiro delay. At time is slowed down by gravity. So this is an effect that was discovered by this man Shapiro in the 1960s, and with the double pulsar, we have an extremely precise test of this prediction. So that tells us that space-time is curved, and what will happen with these kind of systems in many years after my retirement, which is not imminent, but it's also not a billion years away, which I'm kind of grateful for. I think my students are maybe even happier. Is that as these 2 stars go around one another, they emit gravitational waves. So this is the main topic for tomorrow. Again, I'm touching on dangerous territory. And we know that Einstein's theory for gravitational waves is fine for a very long time, since the 1970s, because we saw another double neutron star system called the binary pulsar in 1976, and since then astronomers have been tracking this, and we know that the orbit of this object shrinks at the rate that it's released. So we know that that theory works, but of course, as you all know, because you're here in like science, I think maybe you're just here for a drink, in which case maybe this was a mistake. 4 quid you pay for the ink and what you want to drink. So, of course, you know that we have now detected gravitational waves, so if you haven't signed up before, you're missing out. I'm not going to talk about that. But these double pulsar and the binary nucleus the binary pulsar are going to get drawn closer and closer together. And so here, the final part we're going to talk about is what happens when they come together. So they're gradually drawn together as gravitational waves are emitted. And then, in the final flurry, they come together. And so one of the things we're working on is to predict what would that look like in terms of gravity, and what happens to this extreme matter, these 50 billion elephants, when they crash together. So I think, maybe, a movie, so let me just explain what's going to happen before you push it. So these are the two neutron stars. What I'm going to show you is just a rendering of the density. So these are just very high density regions where most of the mass is. They're going to go around and around and crash together. The colours will change. When the colours change, the density is small. And the reason we're doing this kind of thing is twofold. We want to predict for future gravitational wave experiments what this kind of thing will look like, so we know what we're searching for. And we want to test what happens to this extreme matter when we crash things together. And then, of course, we also want to burn as much supercomputer time as we possibly can. So this simulation I'm going to show you took a couple of months on one of the largest supercomputers in the world. And then you're going to look at this and say, what? Right. So let's run it once. Maybe it's not going to work. No, so there you go. Didn't work. That's why we should have tested this before. Maybe I just can wave my hands and whatever while they try to fix it, or maybe I'll just. Anyway, so there you go. That was it. It took several months. On the largest supercomputer in the world. Millions of pounds, literally. I can throw those two by hand. You learn something from that, right? I think I have some experience in giving presentations and things going wrong. I know you should never, ever, ever let anyone use something to simulate on their own laptop. Always have your own setup to use it. You should never trust it. But I'm running a confession session. I've got a huge 4 cards, 4 card stretch, so that's what we have to stay with. It's wonderful work. He's apologized. I actually apologize to people who come to put up with me for a little longer, but actually this simulation is completely pointless. Just show some red blobs whisking around and that's it. No need to see it. Not going to make you any more or less excited about science. Maybe. Anyway, so the point is, why is it so very, very difficult? Well, it's so very, very difficult because if you want to do this kind of simulation, you want to track how these waves go off the object, but the waves have an incredibly long wavelength. And you work out something that moves at the speed of light at the frequency of something like 1,000 hertz, so 1,000 oscillations per second, has a very low wavelength. So you need to resolve that with numerical simulations, large things. At the same time as we have something that grows 14 orders of magnitude, 10 to the 14, over 10 kilometers in density. Okay? So you need to track both the short and the large scales. You can give up, just show that last slide. I don't care. So we'll go back and it's all there. And so you try to do all these things, and at the same time, the level is always in detail, and so you're trying to do this in Einstein's general theory of relativity. The gravity is void. So space and time evolve as you go. Okay? He's not going to succeed. So maybe if he had shown that last slide that we flip forward to again, I could have talked to you about that. So What I used to do, let me get to the punchline, then I'll sit down. If you finish it, you can watch the video some other time. If you send it to you, then whatever. It's something like 60 megabytes, it's nothing for me, not a computer, but too much for that. So, I've talked about all these things. They're completely irrelevant to you, other than a bit of trivia that maybe it's not that important. But let me ask you a question. How many of you are wearing jewelry? So I know where I can pay for some. How many people are wearing silver and gold? Silver and gold? And where do you think it comes from? Here's my published question. Where does the gold come from? The jewelry. Yes, it's very good details. So where do you think? Supernova. How many people think that gold comes from supernova explosions where I started the journey? No one, not even just one guy in the back, two, okay. That's not very impressive. Okay, let me go. The highest atomic number element that is built in nuclear synthesis in the early universe. Not very impressive. Okay? Stars burn material up to carbon, roughly. Carbon 12, gold is much higher. But you're right that some of the heavy elements, gold, silver, and so on, that we have, are created when stars run out of nuclear fuel and explode in the supernova where I started. But we've learned over the last decade that this isn't enough. If we want to reproduce the kind of amounts of heavy elements like gold that we have in the solar system, supernova explosions is enough. We need more. So where else do we get these hot, dense environments? Well, the answer is the neutron stars collide. So we've learned over the last few years that if you want to explain all the gold, in fact, pretty much every single atom that makes up our bodies, you need to understand what happens when neutron stars collide. So I think that's useful because it's the